Now we will continue seeing the dielectrics in the way as Feynman did in his Feynman lectures. Here we have our parallel plates, the Q positive, Q negative, the dielectric. Here we have the positive induced charges. We have defined in previous videos the dipole moment, electric dipole moment, that is the charge times the distance. Let's call it the Greek letter D, as Feynman did. If we want the dipole moment per volume, and we have, let's say, n being the number of charges per volume, then our total electric dipole moment per volume would be n times the charge times the distance, and the Greek letter D. Then this dipole moment is in the direction of the distance, or in the direction could be of the electric field. So if we have a uniform electric field in the surface, there is no movement or change in the charges or in a charge density volume. But if there is no uniform electric field, then there will be some areas. Let's say that here we have more electric field, then there will be some areas in which the charges are moving more than what they are leaving, and so we have a change in the charge volume density. These charges that are induced, these negative charges that are induced here due to this positive plate, these would move a distance from here to here. This is our distance D, and this will result in that these positive charges will move this distance, so this move inward and this outward. So this surface is called the polarized surface, and has a surface charge density sigma polarized, and this is negative, or has the opposite sign as the sigma free. Sigma free is the surface charge density of this parallel plate. So this is the surface, this is the polarized surface. If we want to know how much charges are flowing through this polarized surface, again we need to take the component that will be perpendicular to the surface. So we would take the area vector, or you multiply times the area and you put the n vectors, that mean the normal vector. So the charges that would be flowing here would be the integral of the charges of the surface times surface charge density times the area. Now if we have that the electric dipole moment per volume is this, we also have that here we have the charges Q, we have some number of charges per volume, that is n, these are charges per volume, and we have these charges, let's multiply it times the volume, so times area and times distance. These are all the charges that we have in this surface, in this polarized surface. If we want this, we want the surface polarized charge density, then we divide these, that are the charges, by area, and so we would have the charge per area. So charge per area is the surface charge density. In this case would be the polarized charge density, that is equal to N times Q times D. So the surface polarized charge density is exactly the same as, let me call this big P, that is the electric dipole moment per volume. So this is exactly the same. So now we want to see the charges that will be flowing through this polarized surface. So it will be the charge density, the polarized charge density, times the area will give us the charges. So these charges are flowing and they are leaving behind the same amount of charges, just as with the opposite sign here. And now we can think of these charges that are moving. We can put this as with P, for example P, like this P, and N dot A. So we don't put it as the vector notation. You can put it like this, as Feynman did. And you can think of these charges flowing through here as if it were a volume of charges moving, or that these charges are moving due to a volume. So we have here a volume of charges. We have the rho, that is the volume charge density. This volume charge density would be the charges per volume. So the charge would be the rho, that is the volume charge density, times the volume. It would be an infinitesimal amount, it would be infinitesimal charge. So we could take the integral of this and it will give us all the charges that would be moving. So we have that the negative of the could be the electric dipole moment per volume dot the normal vector times the area is equal to the, this is the this is the surface integral, because we are integrating with respect to the area. You can also put another integral here, and here we are integrating with dV, so this is a volume integral, or you can put a triple integral here of the volume charge density times dV. Now, whenever we have this shape of this is a vector field dot this could be the normal vector with the area. We can put this by the mathematical theorem of Gauss. We have that the surface integral of a vector field, in this case the electric dipole moment per volume, dot to the normal vector dA, is equal to the volume integral of the divergence of the vector field, divergence of the electric dipole moment per volume dot dV. So here we can write this as the volume integral, or volume integral of the divergence of the electric dipole moment per volume dV is equal to the volume integral of the density of the charges induced times the volume. So we have the same triple integral in dV, so that means that the inner part, or the integrand, is the same. And here I forgot to put the negative sign. So we have that the charge density per volume of the induced charges is equal to the negative of the divergence of the electric dipole moment per volume. So that means that if we have an electric field that is not uniform, we would have a volume charge density induced that would lead to charges induced flowing through this surface induced, and that density would be the same as the divergence of the electric dipole moment per volume that is in the same direction as the electric field. So if we take the divergence of the electric dipole moment per volume, we get the charge density. Now we will use this in the next video to come up with the electrostatic equations with dielectrics.